In today's lesson, we're going to talk about standard F3 in rotational inertia and dynamics. When we talk about inertia translationally, we're talking about an object's resistance to changes in its linear motion. If we instead talk about an object's rotational inertia, we're still talking about changes in it, or resistance to changes in its motion, but here it's rotational motion instead of. So now we have two different types of inertia. One translational for linear motion and one rotational for rotational motion. When we look at the units for rotational motion, the units are kilogram times meter squared. You'll also sometimes hear me refer to rotational motion instead as moment of inertia. Let's talk a little bit more in depth about rotational inertia. When you talk about an object's rotational inertia, the rotational inertia depends on the distance its mass is from the axis of rotation. Objects with mass closest to their axis will have a small rotational inertia. On the counterpoint, objects with without their mass far away from the rotational axis will have a larger rotational inertia. If you look at these two diagrams, you'll see a person on a rotating chair. In one scenario on the left, the person has the masses held far away from the rotational axis. This means the person on the left has a large rotational inertia. The person on the right pulls the masses in. In this scenario, the rotational inertia decreases. That means the closer the masses are to the rotational axis, the less rotational inertia it has. When you talk about rotational axis, though, you have to be very clear about it. An object can rotate about any axis through its body. Generally speaking, most rotational axis for any unconstrained object happens about their center of mass. But if you have a pivot, any spot where the object can rotate about by constraint, say like by a hinge, that means you can pivot an object basically anywhere along its axis. Every different rotational axis will have a different rotational inertia for the same object. That means any object can have an infinite amount of different rotational inertias depending on how that rotational axis is placed and how it configures its mass relative to each other. And again, anytime that we talk about an object's rotational axis that's not center of mass, we refer to that as a pivot. In your reference tables, you'll see this equation. This equation relates mass and position to rotational inertia. So you'll see here on the left, they give it as an antiderivative, and they say that the antiderivative of position squared dm is equal to inertia. Or if you have discrete masses at discrete positions, you could sum up all the masses in their locations by doing the sum of mr squared. When we talk about rotational inertia, again, algebraically, mr squared, and then if we talk about it using calculus, that is the antiderivative of r squared dm. These two equations, though, you have to be looking at your situation to understand which one to use. Just if it's all point masses, it's the one on the right. If you're looking at a continuous mass or a mass that changes with position, you're going to be using the calculus-based version. Let's do an example of rotational inertia using an algebraic situation. In this situation, we have two masses located 4 meters apart. You have a 2 kilogram mass on the left and a 3 kilogram mass on the right. And we're going to see what the rotational inertia is if our pivot is going to be on top of the 2 kilogram mass. In this scenario, we're going to sum up all of our masses in the radius distance that they find themselves. Now, the 2 kilogram mass doesn't contribute at all to the rotational inertia because the radius is 0. But the 3 kilogram mass, that is 4 meters away. So we use the equation mr squared, and we have a 3 kilogram mass and 4 meters away. That's 3 times 4 squared. And we find that the rotational inertia about the 2 kilogram pivot is 48 kilogram meters squared. Bear in mind that this would be different if we had the rotational inertia at any other location, or the pivot, at any other location.